Hi, thanks for tuning in. My name is David Richter, and this is some work that I've done recently with an undergraduate of mine, Theo MacMillan, and a postdoc, Charlotte Wainwright at the University of Notre Dame. The title is a Lagrangian cloud model for the study of marine fog, but this is actually one small part of a big effort of the sea fog campaign led by PI Joe Fernando, which I'll describe here in just a second. If you're interested, this is talk 4.5a, and I will be available from 11:10 to 11:15 to answer any questions or to discuss this in any more detail if you're so inclined. Okay, so the sea fog field campaign is sort of motivated by the fact that marine and coastal fog are really difficult to predict and model. And they also have a lot of societal impacts, on transportation, visibility, economic losses, and so on. And so this was done on the east coast of Canada near Newfoundland, where there's some of the highest prevalence of fog in the entire planet. And so the colors in the background is sort of percent of the time that's actually covered in fog. And near the Grand Banks, somewhat famously, we have a lot of fog. There was a field campaign from September 1st to October 8th in 2018. There were several field sites and other sort of monitoring stations on the coast. And there was also a ship, the RV Hugh Sharp, making measurements. And these are, these transects in magenta down here. And the ship was outfitted with all, a whole host of different measurements for measuring sea surface properties, atmospheric properties, as well as the fog when if and when it encountered it. And this is, the overview of this is actually in a BAMS article, which is in press right now. My focus on this, though, is actually on the numerical modeling aspect of it. And even within that, it's only on one subset of that. So we had a part of the team was doing mesoscale modeling. And so this is COAMP's visibility forecast, sort of the mesoscale forecast for one of the days that we actually did encounter fog. And then at the same time, we're also doing microscale simulations. So these are turbulence resolving large eddy simulations using CM1 and using sort of typical bulk single moment microphysics. This is, these are both from papers which are in press right now. And actually this work over here is actually part of a talk that's later on in this session by Charlotte. And so I'll leave that to her and you can contact her with any questions about that. Where I fit into this is actually developing a Lagrangian approach to doing fog modeling. And so there's sort of a method, a Lagrangian method for doing cloud microphysics called the super droplet. This was coined by Shima et al. In 2009, the Lagrangian cloud model. It's growing in popularity among the cloud physics community for being a really nice way of tackling some of the difficulties associated with modeling clouds in both micro and mesoscale models. And so this is a snapshot from shallow cumulus from Shima et al., where these colors are actually colored dots, each representing a parcel of cloud droplets. Well, the nice thing about these Lagrangian cloud modeling approaches is that they can have seamless treatment of condensational growth, aerosol activation, drizzle and rain formation. In other words, you don't actually have to sort of bin them as either being rain or cloud or aerosol. You actually just have a seamless evolution of an individual droplet as it progresses from one to the other. It also doesn't suffer from numerical diffusion like bin microphysical models do, because of the advection term through radius space. And as a result of these, you can actually just somewhat seamlessly track the DSD evolution. And in particular, you don't have to prescribe one a priori, so like the log normal one that's often assumed for bulk microphysical models. You're assuming a cloud's droplet either number or the distribution itself, which can prevent you from actually studying why different DSDs actually show up in reality, which, as I'll show later, happens during the sea fog campaign. And finally, you can actually, from the Lagrangian point of view, you can actually apply hygroscopicity on a per droplet basis. So you can start to investigate, what if all of the droplets have different don't have the same hygroscopicity? What if they actually have different solutes, right? What if they're coming from marine aerosols versus continental, which is again something I'll show as part of this work here. So in our case, we're using the enthalpy model, which is a model developed, an LES model with Lagrangian droplets developed in our group over the years. And we've done a lot of work on sea spray. And we've actually now, in this case, taken it and adapted to looking at marine fog. And so this is a snapshot taking it out of the simulation, which I'll be talking more about for the rest of this talk. In the background, the color here, right? So this is, I should first say, this is LES of a shallow fog layer. So this is, 30 meters tall. The domain is, only 120 or 130 meters, so it's actually quite small, which I'll describe in just a second. The background fields of velocity, temperature, and humidity are being solved using LES, and so these red contours here are the supersaturation, so this is sort of excess moisture above 100% relative humidity, and these dots, right, each of these dots are a super droplet, and each super droplet represents a large ensemble of real droplets, right? So there's no way that we can actually track every single droplet and aerosol in a domain, even a small domain such as the one that we're focusing on. But what we assume is that locally speaking, there might be a million droplets and aerosols all with the same property. So, this one has a radius, a temperature, a position, a velocity, and so on. And that represents that for a large number of them. So that's the multiplicity is how many each of these super droplets represents. In this picture here, they're colored and scaled in size by their radius. And so you see up here a lot of unactivated aerosol particles, and down within this supersaturated layer, the fog layer, you actually see some large ones. And even within it, you have some heterogeneity due to pockets of dry air, entrainment from the top, and so on. As I said, we're doing large eddy simulation of the background flow, and then that's what drives the evolution of the Lagrangian particles. So the particles are each solved, its position changes according to its velocity changes according to F equals ma, where they're feeling the hydrodynamic drag of the turbulence around them, but they're also experiencing gravity. Their temperature and radius are interlinked because, when a droplet is evaporating, it's cooling. And so we're solving the Kohler equation. So we have the solute effect, and so this is where hygroscopicity comes in. We have the droplet curvature effects taken into consideration, and there's full coupling with the surrounding flow. So supersaturation can be sort of mopped up by the presence of droplets, and vice versa. If the droplets are cooling, then they actually cool the air around them, and vice versa. We have long wave radiative effects because long wave cooling is very important for fog development and maintenance. And collision and coalescence is an option within the code, but we actually don't have it turned on here because we actually purposely focus on condensational growth only. So the case that we study, or the one that I'm going to talk about here, is really we want to look at the droplet size distribution, the DSD response to realistic aerosol spectrum. And so we actually base the simulations on shipborne sea fog measurements when the ship encountered fog. So we set it up with a shallow inversion. So this is the water vapor mixing ratio. This is the potential temperature with a shallow inversion at 30 meters. And this is sort of inspired by some of the measurements taken from the ship, from some of the soundings. We use very high resolution, numerical resolution, so at 1 meter or less throughout the domain, because this has been seen to be critical for actually getting the turbulent transport of the fog right. What we have is sort of a 130 by 130 meter patch, which we say suddenly encounters a lower SST. So we let turbulence spin up, and then at a time an hour into the simulation, we drop this sea surface temperature underneath it, as though this saturated particle has crossed an SST gradient. And so it goes from 284 to 282, which is sort of a typical transition seen from the ship. At the same time, the droplet aerosols, the aerosols are initialized using a measured dry aerosol spectrum from the ship. So the CFOG data here is in the green lines. This is the dry aerosol size. This is the PDF. And so what we do is we say, all right, we're going to approximate this as being the sum of two log normals, one associated with coarse mode. So these are sort of marine-based, very hygroscopic salt-based aerosols. That's the peak over here. And then an accumulation mode. And so this is much lower hygroscopicity associated with more continental origin. And so what we can see, if we take this black curve, which is the initialization, but we actually separate it into, or we look at the distribution of what we're calling the coarse and accumulation mode in terms of the critical supersaturation. We see that the coarse mode has much lower critical supersaturation than the accumulation because we're saying it's marine salt, which has a much higher hygroscopicity. And likewise, it has a much larger critical diameter when compared to the accumulation mode. So this is what we start with. Again, one of the nice benefits of using the Lagrangian model is that we can actually have different hygroscopicities within the same simulation and watch what that does to the DST. So if we look at the evolution of fog, so these are the time height transepts of this is on the top here, liquid water mixing ratio. This is the number concentration of everything, aerosols and droplets. This is the mean droplet radius, and this is the supersaturation. We see that after about 5 hours is when the fog develops. Fog, being defined here, this dashed line is the 0.01 grams per kilogram level of the liquid water mixing ratio. And we can see some interesting patterns of the number concentration. This has to do with entrainment going on at the top. We can see, that there's within the fog, there's actually a pretty sharp vertical gradient of the mean droplet radius, as you might expect, due both to entrainment at the top as well as gravitational settling. The largest droplets are at the bottom, and they're on the order of 10 to 12 microns, but near the top, they're actually quite small. And then we have sort of a consistent supersaturation levels of about 0.1%, which is somewhat large and probably due to the limited number of super droplets that we have in the system. So, it's sort of somewhat of a numerical artifact, but this is something that we're looking to test with larger numbers of super droplets. But as I said, really what I want to focus on in this talk is the evolution of the DSD. And so on the top here, this is an animation on the bottom actually of the DSD as time is going through. And so as you see the fog developing, you actually see some very interesting features develop inside the DSD. And I'll let it start over here and kind of describe it as it happens. So you start with the accumulation peak and the course mode peak, but then once you hit about 5 hours, you start to see this peak shoots off to the right, and then you see the development of a sort of a third peak. And so you have a peak here, and then you have sort of what was the accumulation mode, which hasn't really gone anywhere. And so if we plot this on a wire diagram, this is the exact same on the top here, the exact same thing that was shown in that animation. So here's this initial droplet spectrum, which we're basically taking from the measurements. And here it is as it evolves. Here's the evolution or the development of the peak out to the right. Here's the development of that peak in the middle. And then here's, again, what is basically the unactivated accumulation mode particles, which are just kind of floating around the simulation, and which develops over the, this 8 or 9 hour simulation. If we actually take shipborne droplet measurements from the FN-120 droplet monitor on board the ship, what we see is there's actually a trough, right? There's actually a bimodal distribution seen from the ship. So we have a peak here and a peak here. So this is, a peak somewhere between, 5 and 10 microns. We have another peak around 20 or 25 microns with a trough, which is actually located in almost the same place. And so this fairly simplified simulation, this LES of the fog, is actually getting some of the salient features of the measured DSD. And so then we say, all right, well, what's happening in the simulations which can result in this? Well, this answer is actually somewhat simple. If we take the full droplet DSD, and so this is coming, if we take this last time slice here and we plot it by itself, this is again now a log of the PDF versus droplet diameter. This is the DSD. The dotted line is the full DSD. So here's that accumulation mode peak, here's this sort of middle one, and then here's the third one. But if we actually break this into, this is kappa, the hygroscopicity, if we break it into the high and low, well, the answer actually pops out at us. This peak over here is due entirely to the course mode, and then this double peak here is due entirely to the accumulation mode. And so what's happening, right, and this is shown down here, this is the fraction, so 100% of everything up to here is accumulation mode, and everything over here, 100% of this is the course mode. And what it says is that the largest peak is just accumulation, or sorry, these very hygroscopic particles growing to 20, 25 microns. This peak in here are activated accumulation mode, but they only get to maybe 8 microns. Something very interesting though is that if you actually make the same sort of plot, again, the dotted line is the total DSD. If you actually split this into activated versus unactivated, the peak to the right, despite being these very hygroscopic course mode aerosols, they're actually all unactivated technically, or nearly all, right? So, only 20% of them are activated. And the reason is not because they're not taking on water. They're definitely taking on the supersaturation and growing in size. It's just that their critical sizes, their critical diameters are so large that these droplets take on more and more water. So in that sense, they are active, but they actually become so large and drop out before they can actually achieve their critical diameter. So if we define activation on critical exceedance of the critical diameter, they actually technically don't reach. But then this peak here are, as we said earlier, are actually activated aerosols. So what's happening is that there's a limited number of these course mode ones, and so those grow, that creates the rightmost peak. Because there's a limited number of these, many of the accumulation mode starts to exceed their critical supersaturation and activate as well. And then we have a third peak here, which is due to unactivated accumulation. Okay. So instead of me kind of reading through my summary, I thought it might be fun to have my 10-year-old daughter, Jolene, come and do it for me. So I'll let her recap everything that we've discussed here.
A Lagrangian cloud modeling approach has been applied to the sea fog campaign. LCMs have several different advantages to traditional approaches. Seamless evolution of DSDs, activation and preset, no numerical diffusion, can explore hygroscopicity and aerosol processing. Physical mechanism behind observed bimodal droplet peak, limited number of coarse mode aerosols, large hydrated but unactivated coarse mode aerosols common.
Okay, and with that, thank you so much for tuning in. I'm happy to take any questions either during the session or email or anything else. And this is work that's currently in press in boundary layer meteorology. Thanks so much.